This section 3.4 was all about, we started with looking at velocity and acceleration, how it relates to position, but starting to look at the derivative as a rate of change. I'm hoping that the amount of time we spent on that, we spent a couple days on that, that you're okay with that. Here's one example of looking at a different rate of change. Okay, other rates of change. So we have a circle. You have to consider a situation that where a circle is changing radius. The radius of this circle is changing as you go here. Okay, and you want to know how is if you write the area as a function of the radius, what does the derivative get you? Okay? Okay, so you have to imagine a circle getting bigger. I put those other little dotted blue lines just for a kind of a reference, frame of reference. If you write area how it's related to radius, which you know already, what's the area of a circle? Area. Pi r squared, right? You're already ahead of the game here, right? You can write it as a function and say a of r equals pi r squared if you want, just to emphasize that it's a function of r. The area as a function of the radius. If you find the derivative of this, in other words, if we write now a prime of r, the derivative with respect to r, or of course just a prime, it's 2 pi r. Well, because this is a constant, right? That's a constant. And the derivative of something squared is 2 times that something. Okay? Do I need to close the shutters?
Probably.
You have to think about what this represents in this situation. Okay, if you go back to the picture, this is the rate of change. If this is a function for area, this is the rate that the area is changing as compared to the radius. This tells you how fast is the area changing as the radius changes. If this is measured in, what would that be measured in? We got the radius is measured in. Did I put some units in here? I probably didn't say that, did I? Oh, I did. Yeah. Area would be in inches squared. So what would this be measured in? What would it be measured in? The derivative of that? Well, it'd be a little bit. I'm not getting ahead of myself and answering this question here. I guess it would be inches squared per inch, right? Just like up here, if you have something that is measured in meters and you're comparing it to seconds, the derivative is meters per second. The units are whatever this is measured in compared to whatever that is measured in. So if the area is measured in inches squared and the radius is measured in inches, it would be inches squared per inch. I guess you could simplify it to inches, which is hard to think about. This maybe makes more sense. Think of it as inches squared per inch. It's telling you how much area are you gaining per inch of radius that you gain. Okay? This is the area gained per inch of radius. It's like the speed that the circle is getting bigger. It's hard because you're not comparing it to time, you're comparing it to the radius. It's measuring how much area are you gaining per inch of radius. So if you go from, let's say here, you go from the area of that circle is pi. When it's pi, it actually displays it as pi in this program. But if you change that from 1 to 2, this would be 4 times pi. If you go from here to here, think about how much area you're gaining. Gaining all this area in this second ring here. Okay? For that 1 inch of radius that you've gained all this area here. Is that the same rate as you go from here to here? When you add 1 more inch of radius here, do you gain the same amount? No, this is way more here, right? The farther out you go, the more you're gaining every time you add an inch there. Okay? At the beginning here, you're hardly gaining anything, right? You add that, you gain this little ring. But if the circle's larger to begin with, you're gaining quite a bit. So it's not a constant rate. Okay, this is not a constant rate here. This rate of change changes as you go, but all it is a measure of is how much that is changing as compared to this. All right? Anytime you have a function that compares two things, the derivative, if you have a function and this is measured in inches squared and this is measured in inches, those are going to be the units. Before we had a function that was, you had position, right? Position, and we had time, right? We're using S. S is a function of t. If S is measured in meters and this is measured in seconds, then the derivative of that, S prime of t, is going to be meters per second. It's the units of this compared to the units of that. Okay, whatever we happen to be using as a starting function here. Can you think of some function of one thing as compared? Think of two things that would be related, where something is related to another thing. What's that? Can't hear you. Growth of a tree or something like that, now that you're all staring out the window? Height of a tree? You're not, I'm glad. My own fault for putting the screen right next to the window. Height of a tree as compared to time. If you measure the height of the tree as compared to time, this is meters, and what might be appropriate unit of time to measure the height of a tree? Years, probably. If you wrote this as h of t, a function h is a function of t, the derivative would give you, what would the derivative give you? Yeah, it's going to give you meters per year, and that's going to be the rate of growth of that tree, right? The rate that the height is changing as compared to time. The derivative is the rate of change of whatever function you have. All right? Are we okay with that idea?